NASA's promise to return to the moon this decade is a captivating headline, sparking the same sense of wonder that fueled the original moon landing. Yet, beneath the dazzling surface, a complex story unfolds, one riddled with uncertainties and ambitious leaps of faith. The Artemis moon landing is a prime example. While the target date of 2024 was fueled by political ambition, the technical realities painted a different picture. NASA was forced to reassemble a plan, relying on recycled designs and untested technologies. The Space Launch System, SLS, a product of these hasty decisions, was touted as the key to the lunar return. However, the SLS itself could barely reach lunar orbit, let alone land on the moon. This meant that the landing itself, the very crux of the mission, was left as an open question. Enter the private sector. NASA, recognizing its shortcomings, turned to private companies for a solution, offering a hefty prize for a lunar lander. The race was on, with SpaceX emerging as the winner, their Starship concept promising a revolutionary solution. Colossal rocket capable of carrying 100 tons to the moon or even Mars. But here lies the rub. Starship's impressive capabilities are heavily contingent on a crucial, untested element: orbital refueling. This means that Starship would need to rendezvous with a space-based fuel depot in low Earth orbit, a feat never achieved before, and one that relies on a complex series of assumptions and technological advancement. Question remains: how exactly will SpaceX achieve this seemingly impossible feat? Their answer, much like NASA's, seems to be, we'll figure it out. This figure-it-out mentality, while indicative of the spirit of innovation, also highlights the gap between the grand vision and the practicalities of achieving it. While the Artemis mission holds immense promise, it's important to acknowledge the unknowns that shadow its path. The moon landing, a symbol of human ambition, now stands at a crossroads, reliant on a series of improbable feats, yet fueled by the hope that ingenuity and determination can bridge the gap between dream and reality. The Artemis mission, NASA's ambitious plan to return humans to the moon this decade, promises a new era of lunar exploration. However, beneath the surface of this grand vision lies a complex tapestry of technical hurdles and unanswered questions. While the headline-grabbing goal of a lunar landing captures the imagination, the path to achieving it is littered with challenges that raise serious concerns about the mission's feasibility. At the heart of this complex puzzle lies SpaceX's Starship, the revolutionary rocket that NASA has chosen as the vehicle to carry astronauts to the lunar surface. Starship boasts impressive capabilities, promising to deliver 100 tons of payload to the moon or Mars. However, these impressive figures hinge on a crucial, unproven element: orbital refueling. To transport a single Starship to the moon with its full payload, a staggering 11 other Starships must be launched into orbit first, just to provide the necessary fuel. This means that for each lunar mission, SpaceX will need to perform a massive logistical ballet, coordinating the launch, rendezvous, and docking of a dozen Starships, feat that has never been attempted before. But the challenges don't end there. The fuel used by Starship, a blend of liquid methane and oxygen, demands extremely cold storage conditions. This poses a significant challenge in the heat of space, where a substantial portion of the propellant will inevitably boil off, rendering it unusable. This means that the actual number of Starship launches required to support a single lunar mission could be significantly higher, potentially exceeding 15. Adding to the complexity, current iteration of Starship, despite its imposing size, is currently only capable of carrying a fraction of its advertised payload into orbit. The solution? The yet-to-be-built Starship V2 promises even greater capabilities, but is currently only a concept with no concrete timeline for development. Even if the fuel requirements and payload limitations are addressed, the mission still faces significant hurdles. Starships will need to rendezvous and dock in space, requiring precise maneuvers and flawless reliability. For the whole system to be even remotely cost-effective, Starships must land back on Earth, allowing for rapid reuse, a feat that remains unproven. And then there's the moon itself. NASA's plan calls for astronauts to travel to a unique orbit, the Near Rectilinear Halo Orbit, NRHO, a long, looping path that only passes near the moon once every 6 days. This unconventional orbit, while designed to improve communication with Earth, creates significant limitations. Landing windows become extremely narrow, requiring precise timing and adding to the mission's inherent risk. The landing itself poses a unique set of challenges. Starship's landing system relies on a complex turbopump-driven engine. It's never been used for an extended stay in space, raising concerns about its ability to restart after a period of inactivity. Additionally, the landing will be fully autonomous, leaving no room for human intervention. This contrasts sharply with the Apollo era, where astronauts trained on real-life flight simulators, granting them the ability to manually land the lunar module in case of computer failure. Starship, on the other hand, will be completely reliant on its software, a risky gamble that leaves little room for error. The Artemis mission, while undeniably bold, is shrouded in a cloak of uncertainty. The technology, while impressive, is unproven, and the timeline, aggressive. Success of this mission hinges on the successful execution of a series of audacious technological leaps, all while navigating the ever-present risks of space exploration. Will the ingenuity of engineers and the ambition of NASA overcome these challenges? Only time will tell. However, the Artemis mission serves as a powerful reminder that even the most audacious dreams are often built on a foundation of unknowns. The challenges that lie ahead are immense, but the potential rewards are equally grand. The Artemis mission, if successful, could mark a new chapter in human space exploration, opening up new possibilities for lunar research, scientific discovery, and perhaps even future missions to Mars and beyond. Starship, a colossal, unprecedented machine, defies manual control. Its sheer size renders a pilot helpless, unable to see the base of the rocket, let alone guide it. Landing, too, presents an immense challenge. Modern computers, despite their sophistication, are prone to failure, as recent landing attempts by India, Japan, and Russia have demonstrated. Even with their extensive expertise, intuitive machines, despite their best efforts, experienced a catastrophic tip-over with their slender lander. The sheer size and unique design of Starship further complicate matters. While SpaceX plans to employ a novel, untested method for Earth landings, attaching the rocket with a giant tower, lunar landings require a robust, reliable landing gear system. This system must be capable of handling uneven terrain, a crucial factor that could lead to disastrous consequences. To top it off, our astronauts will be descending from the landed Starship to the moon's surface via an elevator, a novel approach that adds another layer of complexity. The potential hazards of lunar dust, while not discussed here, further highlight the immense challenges of this mission. Despite these seemingly insurmountable obstacles, the brilliance of NASA and SpaceX engineers shouldn't be underestimated. Their ability to tackle these complex problems, to push the boundaries of technology and innovation, is truly awe-inspiring. We may not understand the intricacies of their solutions, but we can trust in their expertise and unwavering commitment to making the Artemis mission a success.